Advanced Higher Chemist, this one is for you.
I thought, since it's Halloween tomorrow, let's do this past paper question that's all about the colour of blood. Now, I do quite enjoy these random, like, why is this the way it is type using your knowledge of chemistry questions, but I'm guessing all of you guys hate them because they do seem a bit weird and you think, how the heck am I meant to know why a human's blood isn't the same as colour as a spider's blood? But what they've asked here is, using your knowledge of chemistry, comment on why these animals have different coloured blood. So hopefully you've noticed by looking at this that all of these structures are transition metal complexes. So this should let you know that what you're meant to talk about here is the colour of transition metal complexes in the context of the colour of these bloods. So let's get into some chemistry. When it comes to transition metal complexes, the colour is always caused by D to D electron transitions. So essentially, this is where an electron gets promoted from one d orbital to another one. So energy is absorbed when the electron is promoted, and that amount of energy corresponds to a wavelength within the visible region. However, it's not the wavelength that's absorbed that is seen, it's actually the complementary colour that is observed or seen. So that's the wavelength that's basically being transmitted. So you don't see the colour that's absorbed, you see all the colours of light that are not absorbed. So if you think about it, if the colour's been absorbed, it's like it's been removed and you can't see it. This is where your colour wheel is your best friend. So if a substance absorbs purple light, then we see it as being green. So all those green trees you see in leaves in the summer are actually absorbing purple light. So our leech's blood that is green is also absorbing purple light. Because the spider's blood is appearing blue, that means it is absorbing yellow light. Now, the colour of the blood can also actually tell you how big that energy gap must be for that electron to be promoted. If you have a shorter wavelength being observed, then it means a longer wavelength has been absorbed. Because wavelength and energy are inversely proportional, that means that if you're absorbing a longer wavelength, your energy gap must be smaller. And then vice versa. If you've got a large energy gap, it means you're going to absorb a short wavelength, and then it means you'll see a longer one. So all of these bloods have different colours, which means they all must have different sized energy gaps. But why are their energy gaps different? Well, this energy gap actually only appears when the d orbitals get split. The d orbitals are usually all degenerate, equal in energy, but certain things cause them to split in energy into this 2-3 formation. If you get different degrees of splitting, you'll get different energy gaps, which then gives you different colours. What affects the splitting? The type of ligand attached to the complex affects the splitting, the oxidation state of the metal affects the splitting, and also the geometry of the complex can affect the splitting. The splitting happens as a result of the repulsion of electrons around the central metal ion. So the way I think about it, the more negative charge that's coming towards the ion, the more repulsion you're going to get. The spectral chemical series can help you with working out the degree of splitting that different ligands cause. The strong field ligands are the ones that cause more splitting, where the weak field ligands cause less splitting. Oxidation state also affects the degree of splitting, and it's generally the fact that higher oxidation states cause more splitting. At advanced higher, you wouldn't be expected to know which geometries cause more splitting than others, but the geometry is really related to the coordination number. So even talking about the different coordination numbers of the complexes here would be additional chemistry you could discuss. And that's just all focusing on the central transition metal ion and how it's causing the colour. However, if you've also done organic chemistry already, you'll maybe have noticed that these ligands have conjugated systems. So that means the ligands could be contributing to the colour as well. But this video is getting too long now, so I'm not going to go into that. I'll save that for another time. Happy Halloween!